So we've got a box being pulled across the floor with a rope. And it asks what is the applied force. So I'm going to call this applied force, even though it's a rope. It could be called tension as well, but I'm just going to go with the wording of the question here. All right, so it's just moving to the right, and there's a constant velocity there, so the forces are balanced. So I'll go ahead and draw a free body diagram. I will first define my directions, though. I will call up the positive y direction, and I'll say the right is a positive x direction. Okay, in terms of my free body diagram, well, you know what? I'll just use the diagram I have here. I'll erase the floor. So that applied force I drew, I'm going to draw the components in for that. And label the vertical component as FAY and the horizontal component as FAX. All right, I'll think about the other forces involved here, which would be gravity, friction, and normal. So I'll start with gravity. And then I'll go with friction. So friction should be balanced with FAX. So those are the only two horizontal components. So use a tick mark there to represent that they're equal. And then there's normal force. So normal force, you have to be careful with. How large should I draw it? Well, I'm going to draw it smaller than gravity because there's an FAY there. There's an upwards component to that applied force. So that cancels out some of the gravity, and the normal force only needs to match whatever's left over. So it's going to be shorter than the force of gravity is. All right. So now I will start the equation writing. So I'll have two headings here. I'll analyze my x direction, and I'll analyze my y direction. So in the x direction, it's just friction and x component of applied. They're equal to each other. So I'll write the magnitude of friction equals to FAX. Okay, that equation is simple enough. The y direction is a bit more complicated. There's 3 forces in total, with 2 of them pointing up and 1 of them pointing down. But they all have to be balanced because of the word's constant velocity. So I'll say that my FAY, well, so y component of applied plus my magnitude of normal force. So those are both pointing up. You add them together, and that's got to equal or balance out the magnitude of gravity, which is the only force pointing down. So these two would be my starting equations. My next step would be to rewrite any term here with its own equation. So the first one's friction. So friction gets rewritten as mu times the normal force. And then the x component of applied. So my x component, if I label this angle as theta, that's the 30-degree angle that it says in the question, then my x component is adjacent to theta. So it would be written as using the cosine function. So FA cosine of theta. All right. Now on the y side, I have FAY. So FAY, That's the opposite side of theta, so I'll use sine, Fa sine theta, plus the normal force. The normal force does not have its own equation, so I'll just copy it down as normal force, equals force of gravity, which has its own equation of mg. Okay. Next, I remind myself of what I'm asked to solve for here, which is applied force. What is his applied force? So that is found on both sides, actually, on my x side and my y side. There's an applied force term for both of those. So what do I do? Do I use the left side? Do I use the right side? Well, it turns out that we have to use both sides and use two equations because there's going to be two unknowns. All of these symbols here, I actually know all the values except for applied force and normal force. I don't know that either. Okay, so normal force is a second unknown. Everything else I know. The mu I know. The theta I'm given, 30 degrees. The mass I'm given. And the g value is 9.8. So two equations, two unknowns. Solve using substitution or elimination. So I'm asked to solve for the applied force. Since I'm asked to solve for the applied force, what I'm going to do is isolate one of these equations for the normal force and then substitute that expression into the other equation. So I'm going to choose the x side. It doesn't matter, you should end up with the same answer, but I'm going to choose the x side to isolate for the normal force. I can do that simply by dividing both sides by mu. So I isolate that for n, Fn, so that I can now take this expression and I can substitute it into my second equation where the Fn is. So I'll call this equation 1, I'll call this equation 2, and I'm saying what I'm doing is I'm going to sub this expression from equation 1 into equation 2. Okay, so I'm going to switch to, I guess I'll go with black now. So this is going to become, I'm going to require a lot of room here. So it's Fa sine theta, that's the first term, stays the same, plus, so this normal force term, I'm going to change that to the expression I've labeled as number 1. So change it to Fa cos theta over mu equals mg. So this is my new equation, which I'm going to isolate and solve for applied force. So one approach would be to just fill in all the values now. So fill in theta and get sine theta. Fill in theta and get cos theta divided by mu, figure out the number for that. And fill in m and g and figure out the number for that. And then collect like terms and isolate. So that's one approach. The approach I'm going to do is to do it all symbolically first. So I'm going to common factor applied force on the left side, because they both have applied force multiplied to it. So factor that out. leaving me with sine theta from the first term, and cosine theta divided by mu for the second term. Okay, so that's common factoring. And now all that in the brackets there, I'm going to move it to the other side with division. So FA will equal to mg divided by all of that. At this point, this is when I like to fill in the values at the very end, if possible. There are some questions where I may do it a bit earlier just for convenience, but this is the preferred method here. Okay, so let's get going on the calculator here. You have to be really careful here when you're dividing by this denominator. You got to make sure you're actually dividing by the whole denominator and not just dividing by sine of 30 and then adding the other term, the cos 30 over mu. That's what ends up happening sometimes if you don't type it in right. You should put the entire denominator in brackets when you fill it out in the calculator, just to make sure that the calculator knows to treat that whole thing as one thing on the denominator. We'll replace mu here with the value 0.25. Okay, so my answer is giving me 49 newtons. So that would be the applied force that Alex is pulling this box in. And that's example 3. So example 4, what if the box from example 3 accelerates at 2 meters per second forward? So basically I want to practice a situation where there's acceleration. So can I preserve anything from the solution here, or do I have to start all over again? Well, the acceleration is forward. It's in the x direction, so that's got to change. However, the y direction, that equation there probably can stay the same because it's not going to move up or down, so the up and down forces are still going to balance. So I'm going to start question 4 now. I'm going to take an eraser and I'll erase some of this question 3 stuff. And I'm going to erase the x. The stuff written under x, because that's going to have to change. It's no longer balanced in the x direction. Actually, better adjust my free body diagram to make it so that they're not balanced. It's going to accelerate to the right. So friction will end up being, well, smaller than the x component of applied force. Okay, so what equation can I write in the x direction then? Well, I can write Newton's second law because it's accelerating in the x direction. Okay, so I'm going to say that F net, the net force, I'll do this in terms of magnitude since there's only 2. There's one left force and one right force. So the magnitude of the net force will be the force to the right, so FAX minus the magnitude of the force of friction. All right, so I kind of squished that in there. F net is rewritten as MA. FAX, the x component of the applied, is written as FA cosine of theta. And then force of friction is mu times the normal force. Okay, so that becomes my new equation to solve for the same problem, but this time the box accelerates to the right. So it's a bit more complicated. The math is the same, though. I still end up with two equations with two unknowns. I still do not know the applied force and the normal force. However, I know everything else. I know the acceleration. Yeah, so it's the same thing. I'm going to isolate one of them for one variable and sub it into the other one. And it's going to take an awful long time. So I'm going to just get Wolfram Alpha to do it, I think. Save myself some time here. So I'll fill in the numbers now, actually. So on the left, m times a is 20 times, acceleration is 2.0. Fa cos theta, so Fa cosine 30 degrees, minus mu Fn, so 0.25 Fn. So that's the equation for the x side. And I'll simplify some of these numbers. So 20 times 2 is 40. And then I'll have Fa cos 30. I'll leave it as cos 30. I won't simplify that. I can type in cos 30 into Wolfram Alpha. That's fine. Minus 0.25 Fn. Okay, so there's equation 1. Equation 2, fill in the numbers here. So Fa sine of 30. That one's nice. Sine of 30 is equal to a half. Plus the normal force equals mg. So 20 kilograms times 9.8 newtons per kilogram. Yeah, I'll just change sine 30 to 0.5. And then 20 times 9.8 is 196. Okay, so that'll be equation 2. So what I'll do is I'll type these two into Wolfram Alpha. I will use A for the applied force. I'll use B for the normal force and see what Wolfram Alpha comes up with. So you won't be able to see me typing it in, but I'll just give some commentary maybe. So I'm typing in Wolfram Alpha, loaded up. 40 equals, I'm going to say A times cosine of 30 minus 0.25 times B. I'm using B for the normal force. Write the word and, A and D. Then I'll type the second equation, so 0.50 times A plus B equals 196. Hit enter. It is thinking, it is computing, and it has given me an answer for A and B. It's telling me that A equals 90, so that would be the applied force. So I'll say enter 1 and 2 into Wolfram alpha. And then we get out an answer of the applied force being 90 newtons. So that's a decent number. I don't know if you recall, for example 3, our answer was 49 newtons. That was to keep it going at a constant velocity. Well, now we need to accelerate this thing, so we need more newtons. So 90 seems reasonable. Wolfram alpha is also spitting out the normal force for me. The question doesn't ask it, but I got it, 151 newtons. All right, so that's question 4 for the acceleration forward. And then it goes on and asks, well, what if the acceleration is backwards? Well, I'm not going to retype all this in, well, maybe I can. I mean, what happens is, so if the acceleration is backwards, that means it's slowing down, and that means it's actually friction that's larger than the x component of applied. So in the equation, I just swapped those two terms. I drew that with the black arrow there. That's the only difference. These two switch places. These two switch places. These two switch places. So I can actually just go up to a Wolfram alpha and I'll just switch the order of them. So copy and paste some stuff, or maybe change plus signs and minus signs. So actually it's not a difficult change, just throwing it in the calculator. So I'll call this example 4B. So the answer to example 4B, it spit me out an answer of 9 newtons, or 9.1 for 2 sig figs. And it's giving me a normal force of 191. So these numbers make sense. 9 newtons is small. It's less than the 49 newtons that was required to make it go at constant velocity. It makes sense that it's less because it's slowing down this time. All right, so that is this question. Basically, we answered 3 questions here. Showed all the algebra for example 3. Showed some of the algebra for example 4A, but did the rest in Wolfram alpha. And then for 4B, you just had to make a little switch there, answered it in Wolfram alpha as well.